All right, so good morning, everyone. My name is Ryan Cott, and I'm a senior.
I'm Rashawn Thangaraj. I'm also a senior.
Hello, my name is Suyan Du, and I'm also a senior.
My name is Joseph Levinston. I'm also a senior.
My name is David Zapata, and I'm also a senior.
Good morning, everyone. We are representing Team 18753 from American Heritage Schools Palm Beach in Florida. Just by a show of hands, how many people lost some money on the Super Bowl this past season? Yeah, clearly we're qualified to talk about this today. We know that the house always wins. In fact, even if you bet against the Jets, the betting gods will find a way to make you lose. The question is, who actually pays the price in these cases? That's the question that we're set out to answer. In fact, we have to understand first, though, why this actually matters in the first place. Just last year, over $150 billion were spent on sports bets. That's an 11-fold increase from just 6 years ago. In fact, 22% of American adults have an active betting account. And for males aged 18 through 49, that is a 50-50 chance. Why, though? Well, in 2018, the Supreme Court repealed the ban on sports bets, and following suit, 38 states legalized sports betting. So, how do we answer this? Well, we created an interconnected model of our three solutions. First, we start with our disposable income model that quantifies how much money people actually have to spend and, in turn, how much they can afford to lose. Second, our gambling loss model quantifies how much, on average, people lose on these bets and put into context with our disposable income model. And finally, to boil down the first and the second model into one understandable metric, we created the Gambling Financial Stress Index for question 3 using Markov behavioral dynamics. To talk about the first one, Rashawn Thangaraj will take over.
So how much can a person actually afford to lose? We start with 3 key assumptions. First, we convert household level BLS data to individual data using age-specific earners per household ratios. Second, we impose a 5% disposable floor. The lowest BLS quintile is 3 to 8% non-essential spending, and a 5% floor prevents any $0 predictions. And finally, we rely on Engel's law, the idea that as income increases, essential spending increases, but as a decreasing share of the income. So for stage 1 is computing after-tax income. For the U.S., we apply 2024 tax brackets and FICA contributions, and then after that, we apply regional state averages. For the U.K., we apply HMRC tax brackets, a personal allowance of £12,570, and a national insurance. For stage 2, we model essential spending. We first perform a OLS regression on the BLS consumer expenditure survey data, 123 observations across 3 time periods with varying income groups and age levels. And we also apply period fixed effects to handle any year-specific shocks like COVID. Our model is on the screen. To model essential spending, we use the log of after-tax income along with the centered quadratic age of the centered around the mean age term of 46.3. This represents a change from our paper. We want to improve our model by pooling across 3 periods of data as well as adding that quadratic age term, which decreased both of our age p-values to 0.005, while originally in our paper it was 0.101. And this slide shows that a quadratic age term actually matters. A 22-year-old young adult has a marginal year-over-year increase of $525 per year of age, reflecting on starting families or increasing healthcare costs. At 50, this drops to a $107 marginal increase year-over-year. At 68, this flips negative, reflecting on decreasing food and transportation costs. And we can see that through the per category drivers table right here. At the start, healthcare drives prices, but later in life, food and transportation brings the essential spending curve back down. Now we have the complete model. To compute disposable income, we take the after-tax income and subtract the regional adjusted essential spending, dividing that by the number of earners per household. We have a lower bound set based on our 5% disposable income floor. And here we can see what this actually means for real Americans. A young adult with a gross income of $20K in the South has only $784 of disposable income, which also hits the 5% disposable floor. A peak earner with a family earning 71K retains around $14,300 or 28% of their income. And a retiree back down to the 5% floor. On average, we found that only mid-career workers retain any sort of disposable income. And everyone else operates on razor-thin margins. Now it's up to Suyan. Now we'll take it to Suyan.
So we replicate our model for UK data as well with ONS data. And we get, of course, again, we get an R-squared of 0.957 with all coefficients being significant. But the most important result here was structural. As you can see, the age coefficient for the US is negative, while for the UK, for the age coefficient for the US is positive, while for the UK, it's negative. Why does the sign flip? The answer here is healthcare. In the US, with the private healthcare system, as you grow older, costs rise sharply with age, while in the UK, the NHS absorbs these health-related costs. For sensitivity analysis, we use a two-pronged approach. First, we use category definition sensitivity, essentially dropping or adding different categories of spending. For example, if you remove transportation, disposable income nearly doubles for peak earners. And essentially, we're justifying why we include these certain categories for essential spending. We also did Monte Carlo jitter of plus or minus 5%, showing that our model is robust. And for our strengths, our four main strengths were, first of all, we use real statutory tax brackets. Second of all of our regression terms were significant. Third of all, we used incorporated multi-year pooling. And fourth of all, we used an age-specific conversion from household to individual. For limitations, the first one was the conversion was approximated. The second is that although we have interregional factors, we don't account for intra-regional variation. And third of all, the UK ONS data does have some overlap for pooling. Now, on to question 2. How much does each demographic actually lose per year from gambling? So our gambling loss model is based on 4 key assumptions. The first one is that the surveys provided by M3 are representative of the nation. The second is that house edge and risk is linear, starting at 4.5% for straight bets, all the way to 20% for parlay heavy bettors. Additionally, since over 84% of bettors exceed 30 bets a year, we're able to invoke the central limit theorem. And fourth of all, based upon assumption 1, we're able to scale our bet sizes to match the known $16.4 billion figure from the American Gaming Association. Now I'll go through our derivations for house edge and per bet variance. For house edge, we start with the standard minus 110 line, which means you bet $110 to win $100. And then using linear interpolation, we get our effective house edge is 0.045, the floor plus 0.155 times the risk tolerance. For per bet variance, we do a similar methodology and we get 0.91 plus 12 times the risk tolerance squared, which is quadratic in risk tolerance. For our 8 demographic groups, we derive the following. First is a beta distribution representing risk tolerance using 2 survey signals. The first one is the chase rate, or essentially the proportion of bettors that keep betting after a loss to try and make up for their loss. The second is the high stakes rate, or the proportion of bettors that bet more than $500 or have bet more than $500 in a day. We also get betting frequency directly from survey data, and we get bet sizes from a log normal distribution, which has a small mean, showing that most bets are small sized, but there's a large right tail of larger wagers, which is also what we see in the real world. And now I'll hand it to Joey to talk about our simulation.
We simulated 10,000 bettors in each demographic group to collect our data. We scaled the per bet individual normal distribution by n, the number of bets per year, and this also scaled our variance, which tells us that for more high-risk gamblers, you're going to have more spread in your winnings or losses year to year. We found when we collected our data that the most at-risk group to lose the most amount of money is males aged 18 through 34, and the least at-risk group is females over the age of 65. Additionally, the probability of a winning year fell somewhere between 30 and 33% for each demographic. Finally, when we pulled all of our data together, we got an annual gross gaming revenue, or GGR, within 1% of the AGA's purported numbers. Now, the median bettor only loses somewhere between $59 and $96 every year. Why is this so much lower than the mean? This distribution is extremely skewed. The majority of bettors are only losing a reasonable amount of money every year comparable to other entertainment costs, while the ones who lose the most drag the mean way, way down. Now, for our sensitivity analysis, we jittered the risk tolerance, derived house edge, and betting frequency by 10% over 1,000 trials, and found that the spread in the results was only somewhere around 14 to 17% for each demographic group, showing us that our model is relatively robust with these conditions. Now, one of the biggest strengths of this model was the fact that we derived our house edge, as Suyan explained earlier, and did not find a value or an existing formula for this anywhere in a book or online. One of the biggest limitations of this, however, was the fact that we sampled bet sizing and bet frequency from independent populations, when in reality they should be quite correlated. Now, we know people are losing money, but at what point is a loss genuinely harmful? We quantify financial loss with 3 different thresholds: 2, 5, and 15% of disposable income. There's an idea in prospect theory where the psychological impact of loss is twice that of an equivalent potential gain. So say I were to bet $100, the minimum amount I'd be willing to risk my $100 to win is right around $200. Now, to facilitate our third model, we introduce a financial stress index called the GFSI. We introduce some names for the thresholds, such as casual, elevated, high risk, and the debt zone. Once you're in the debt zone, your gambling losses are competing with things like your rent or the amount that you're spending on healthcare. And that is very, very bad. I'm going to hand it off to David to explain the next couple of things.
Okay, so we created 3 different functions to account for how different gamblers act. Our first function is meant to account for people who chase for more after initial losses, multiplying their bets by a factor of alpha. For example, we found that young male bettors have an alpha factor of about 1.62. Our second function is meant to account for people who do not chase for more after they lose. And then our third function is meant to account for how a person's future is affected by overuse of gambling, showing that their next year's disposable income decreases quadratically. Now, over a simulated 10-year period, we found that the probability of staying in the debt zone, given that you're already there, is 0.596, and the probability of transitioning from the casual zone to the debt zone is 0.567. Now, other than these probabilities being extremely high, we found that all of our rows and columns differ, showing that we likely have state dependence in our Markov chain. Now, we found that out of the 45.1 million American bettors, the 13.91 million, or around 30%, are in this high-risk scenario. We also wanted to check our findings with the National Council on Problem Gambling and found that our estimate of 2.8% of people in the debt zone aligns with their 2 to 3% estimation, and our estimate of people in high risk being 5.4% lies within their 4 to 6% range. Now, we also found something interesting, and is that retirees are surprisingly vulnerable to losses due to gambling, even though they have the lowest absolute losses. Now, that's going to be accounted for by looking back to question 1, where we found that retirees consistently hit that 5% floor. So, a loss due to gambling, like $200, that wouldn't seem very high to a peak earner, would pass that 5% threshold needed to be considered escalated or high risk easily. Now, here are all of our transition matrices for each demographic. Some interesting findings we had is that younger people had a much more difficult time transitioning from state to state, while older people could travel from state to state much more easily, and this can be accounted for with experience, maturity, other factors like that. Now, for the median young male bettor, $449 per year at 7% real return can account for about $18,000 in foregone wealth over the next 20 years. And if continued expansion in the industry continues, the gross gaming revenue can double to nearly $33 billion by 2034. Now, for sensitivity testing, we changed the threshold needed for high risk, dead zone, etc., and found that even at the highest level of testing, over 20% of American bettors were still in a very risky situation. And we also found that chase rate had the greatest effects in someone's long-term financial stress. And we wanted to make sure our mechanisms actually allowed for value in our Markov chain for state dependence, and we found that not having any of them would make our rows nearly identical. Now, for some strengths and weaknesses we had, our strengths is that we projected multiple scenarios in the industry so we can account for future uncertainty, and that we have and one of our limitations is that we have no quit or exit state, which can allow for long-run exposure to gambling be overstated in our model. Now, I'm going to pass it off to Ryan for our conclusions and key findings.
So with all of that in mind, we can see that the most at-risk group are males 18 to 34, making up about 5.8 million of those in at-risk and generating $6.1 billion in revenue on their own. But we saw a key surprise here. Like David said, with the retirees and also with females, they have a higher vulnerability, even though they may have lower absolute losses. But again, this is because vulnerability is defined by the ratio to disposable income. And also, chase behavior is key, since if we have the chase rate, we see that the dead zone to dead zone probability can decrease by 7%. So with all of that in mind, we have some recommendations for regulators. First, if you set income scale deposit limits, we can help those bettors that want to bet but understand what it means in terms of disposable income. Furthermore, having loss tracker displays and cooldown lockouts can mitigate the harms. But for the funding side, if we put a tax or a wager fee on these bets, then we can use these to re-implement them and reinvest them into education, particularly to teach people about the opportunity cost of betting instead of investing their money, which we saw on average could yield $18,000 in returns for these individuals. With that in mind, that's all that we have for today. So thank you, and if you have any questions, we would love to hear it.
Well, first I'll say you hit 15 minutes on the dot, so I'm impressed for our first team. I can start us with a question, which, yeah, I loved your paper because you have very complete models for all 3 parts, but I want to ask something about the first question. You said you left out shocks like COVID-19 and other events. And I wanted to ask, first off, how you did that. And also, is that something, if you had more time with the model, is that something you would want to do, or is it important to incorporate those shocks when we're talking about impacts of gambling?
So what we did was we applied period fixed effects to account for those sort of shocks. I think in future models, something like COVID, which messed up a lot of people's disposable income, could definitely play a factor into gambling and gambling uncertainty and stuff like that.
So what do you mean by period fixed effects here?
To our regression, we essentially had indicator functions. So like, oh, if we're over 2023 data or 2021 data, that would turn on, and we have like some regression coefficient associated with it.
Okay, so not necessarily periodic, but you had like a variable that accounts for this. Okay.
And I would like to expand on that because if we're trying to predict someone's disposable income within the model itself, the period effects would turn on. But if we want to extrapolate it, let's say future years, then we probably wouldn't necessarily want the COVID data to skew or bias the results because we're not in a recession or some other extraordinary period.
Okay, cool. That makes sense. Thanks, guys.
Any other questions?
All right, thank you. I want to follow up on your question 1. You said you added the age squared term. Why did you do that, and have you looked at your residuals, and what were the patterns you saw?
We looked at essential spending graphs, and basically what we saw is that age wasn't linear as we had in our paper. Due to time constraints, we kept a linear age. But after looking at tables and looking at the data itself, we found that age itself wasn't linear. It was more curved or quadratic as we put on our paper. After the paper, after realizing that we had a p-value of 0.101 and we want to make that term significant, we found more data. We turned it quadratic based on looking at tables of essential spending, and then we found that that seemed to work.
Okay, so I have a question about your regression model for UK. I'm really impressed that you did 2 models. So you used 2 different data sets. And why is the coefficient of age in the essential regression for UK negative? Does that mean that older people have less essential expenses? Like, what do you consider as essential expenses?
So we use 5 main categories for BLS, including things like transportation, rent, food, etc. And like we said, I think our conclusions drawn from the negative coefficient is mostly that in the UK with like their healthcare system, like the NHS, they're able to absorb all the healthcare expenditures that greatly increase essential spending for people in the US, which is also why we saw the difference between the UK model and the US model of like positive and negative. Thank you.
So when you're looking at the tax calculations, retirees receiving Social Security benefits don't have that 6.2% reduction for Social Security. How would that change things?
I'm sure that's like an extra injection essentially to their disposable income, and that's something that we would love to factor in later on because we didn't really account for other sorts of welfare spending as well that some demographics may have, but we love that suggestion and we'd love to implement that in the future. But in general, I think that may affect the quadratic term or the coefficient or the sign of the coefficient as well. Maybe not in the regression itself because essential spending would approximately stay the same, but when we go to our final model to actually calculate the disposable income, that may be an additional factor that we would have to include to add to our disposable income.
We have like 40 seconds.
So very quickly, if you had more time, what more would you like to do? Or what specific things would you like to add to your model?
So one thing we like to do is, for example, for our demographics, right, we split across just age. Simply, we split across age and gender. Of course, there's a lot more demographics. For example, like race. I know there's a lot of studies on like how different races can be affected by gambling in different manners. You can also somewhat split across income level. I think that would be an interesting, I guess, future work. But of course, we would need more data for that, and that takes time to find.
And another thing for our third solution is we would also like to add an addict state and a quit or exit state, because our third model essentially assumes that someone bets continuously, whether that's a large amount or a small amount, but someone may decide to stop betting. But also at the same time, for an addict, their behavior might be different because they're in a perpetual state of chasing perhaps their losses or just wanting more money.
We have to wrap there, but thank you guys for both the presentation and great answers.
Thank you.
So much for the questions.